Testing, can you hear me? All right, this video is public now. So I'm going to be studying introductory statistics again. Last time I studied about discrete random variables. This time I'm going to be studying the next chapter, which is about continuous random variables. Let me change to full screen. So last stream, I was studying about this. Sorry, no. I was studying discrete random variables. I was studying about the different distributions. This stream, I'll be studying the continuous one. And just make a straight line here. Continuous random variables have many applications. Baseball batting averages, IQ scores, the length of time, a long distance telephone, the length of the time a long distance telephone call lasts, the amount of money. Okay. The graph of a continuous probability distribution is a curve. Probability is represented by area under the curve. Curve is called the probability density function. We use the symbol fx to represent the curve. Fx is the function that corresponds to the graph. We use the density function fx to draw the graph of the probability distribution. Area under the curve is given by a different function called cumulative distribution function. Cumulative distribution function is used to evaluate probability as area. The outcomes are measured, not counted. The entire area under the curve and above the x-axis is equal to 1. Probability is found for intervals of x rather than for individual x values. Probability for interval. Probability for one value is equal to 0. The probability for open interval is the same as the probability of closed interval because the area is equal. We find the area that represents probability by using geometry formulas, technology, and probability tables. In general calculus, S needed to find the area under the curve for many probability density functions. When we used formulas to find the area in this textbook, the formulas were found using the techniques of integral calculus. However, because most students taking this course are not okay, I mean, we have studied calculus, so it's not a problem for us. I studied calculus first just for this topic, but I don't think we need it. We begin by defining a continuous probability density function. We use the function notation fx. Intermediate algebra may have been your first formal introduction to functions. Study of probability, the functions we study are special. We define the function fx so that the area between it and the x-axis is equal to the probability. Since the maximum probability is 1, the maximum area is also 1. Continuous probability distribution, probability is equal to area. So we have a continuous function. The probability is the area under the graph. For a continuous function, it's just one rectangular box, right? There's no curve, just one horizontal line. Consider the function f of x is equal to 1 over 20. X is a real number. The graph of f of x, 1 over 20, is a horizontal line. However, since 0 is less than equal to x, which is less than equal to 20, fx is restricted to the portion between x is equal to 0 and x is equal to 20, inclusive. Graph of f of x is equal to 1 over 20 is a horizontal line segment. Area between 1 over 20, where, okay, the area between this line and this line inside this box is 1. Suppose we want to find the area between f of x is equal to 1 over 20 and the x-axis where 0 is less than 2 is 0, where x is between 0 and 2. You just find the area of this. This area is 2. Wait, no, this area is 0.1. Probability between 4 to 15, the area is 0.55. Oh, they did not give any exercises. I think they will give it in the end. Wait, this is a uniform distribution, right? What was this chapter? I thought we were learning the uniform distribution. Uniform distribution is a continuous probability distribution and is concerned with events that are equally likely to occur. When working out problems that have a uniform distribution, be careful to note if the data is inclusive or exclusive of endpoints. The data in table 5.1 are 55 smiling times, seconds of an 8-week-old baby. Sample mean is 11.65 and the sample standard deviation is 6.08. We will assume that the smiling times in second follow a uniform distribution between 0 and 23 seconds inclusive. This means that any smiling time from 0 to and including 23 is equally likely. The histogram that could be constructed from a sample is an empirical distribution that closely matches the theoretical uniform distribution. So x is the length in seconds of an 8-week-old baby smile. The notation for a uniform distribution is UAB, where U is the lowest value and B is the highest value. Probability distribution is 1 over BA, 1 over B minus A. Okay. And the theoretical mean and standard deviation. So the mean is just A plus B divided by 2. This makes sense. Sigma is B minus A squared divided by 12. Okay. This one doesn't make sense. Why is this there? I think we would need to do integration to figure this out. How would integration work with with hold on, uniform distribution? Before I want go any further, I just want to check the definition of variance. It's not opening. Standard deviation, where's the formula for it? X minus mu square divided by n. X minus mu square divided by n. Or what is n in this case? Is it the interval? Can't be, right? What is the what is the definition of standard deviation when it comes to wait, did they define it? Let me see. No, I will have to search it up on my own. So, okay, the definition for the mean could be where the area cuts by 2. So, for example, for a uniform distribution, the mean, let's just B, A, and then B. And then the mean could be like what cuts the area in 2 parts, in 50-50 parts. This is the mu. And the mu is A plus B divided by 2. But how do you measure the spread of the data? I mean, if the data were like this, then it's not very spread out. But like this, it's. You let me think. Maybe an integral from A to B x minus mu could be this. And then divided by the interval, maybe. Maybe, okay, let's say, I mean, the definition of sigma could be this. Minus. But this is just a constant. And let's see what I end up getting. Also, why did I write u here? X. And then minus it with. Is this correct? And then b minus a. But mu is a plus b divided by 2. Mu is a plus b divided by 2. A plus b times. Okay. Then I end up with this, right? That doesn't make any sense. Hold on. No, no. I made a mistake. This square. This would make sense why it's 0. Because it's the mean, right? So all the values minus the mean will cancel out. Like all the values behind the mean, the difference will cancel out with the difference in front of the mean. Yeah, yeah, that makes sense. So this is all wrong. Okay, so I have a square here. Square is going to cause some issues. Or maybe I can just expand the x square. X square minus 2 mu x. Would this make sense? So we have this, which is x to the power of 3. I can take mu out because it's a constant. What is that? So we have b cube. Is this even right? Or did I make it more complicated? Hold on, hold on. Derivative would be equal to outside, derivative of the outside times by the derivative of the inside. I'm left with 3x squared. Does this make things easier? Okay, let's try. P minus A integral, not integral. Evaluating the integral mu over 3. Evaluating this integral. I will take the 3 out and then I'll put P and P minus mu cube minus it with did I make this more complicated? Yeah, I will look at this on my own time. Then mu is A plus B over 2. Yeah, I will look at it on my own time. Maybe there's an easier way. They ended up with this divided by 12. The data that follow record the data that follow record the total weight to the nearest pound of fish caught by passengers on 35 different charter fishing boats on one summer day. Man, there are no answers here. Example 5.2. Actually, yeah, there are answers here. The sample mean is 7.9. The sample standard deviation is 4.33. The data follow a uniform distribution where all values between and including 0 and 14 are equally likely. State the values of A and B. Write the distribution in proper notation and calculate the theoretical mean and standard deviation. So A is 0, B is 14. The mean is 14 divided by 2, 7. Standard deviation is B minus A. 14 minus 0 is just 14. 14 squared divided by 12. Square root that. 14 squared is just 14. And then, so it's just 14 over root 12, right? 4.04. They said example 5.2, it's referring to this example. So, anyways, I think the answer for this is 4.04. I hope I'm right. The amount of time in minutes that a person must wait for a bus is uniformly distributed between 0 and 15 minutes inclusive. What is the probability that a person waits fewer than 12.5 minutes? It's uniformly distributed. It's between 0 and 15 minutes. That is the probability that a person waits fewer than, oh, example 5.4. 12.5, 0 and 15. X fewer than 12.5. The height of the graph is 1 over 15, right? Well, the height of the graph is 1 over 15. The probability is 12.5 over 15. That makes sense. Find the mu and standard deviation. Mu is just 7.5. Standard deviation is 15. So 15 over root 12. 90% of the time a person must wait follows uh, falls below what value? So they want probability of x, let's say b over 15. They're asking us when b over 15 is 0.9, right? 13.5. The height is 1 over 15, 0.5 and 0.83333. This is, yep. Then I have this, which is 4.3, 13.5. Suppose the time it takes a 9-year-old to eat a donut is between 0.5 and 4 minutes inclusive. Then x the time in minutes it takes a 9-year-old child to eat a donut. Then x, it's uniformly distributed from between 0.5 and 4. Probability that a randomly selected 9-year-old child eats a donut in less than 2 minutes is, so this is example 5.5. So why is it slow? Hold on. I'll just start a new page because it's getting really slow. Yeah, I will copy some of my exercises. So example 5.5, x is uniformly distributed between, let me draw the line. Now I don't know why this appears. Okay, x is uniformly distributed between 0.5 and 4. In at least 2 minutes. Child eats a donut in at least 2 minutes. So is that before 2 minutes? They mean within 2 minutes, right? Or do they mean he takes at least 2 minutes to eat it? I think this is it. Wait, let me just be sure. Well, if it's reverse, then I have the height of this is 4 minus 0.5 is 3.5. 3.5 area is 1, so the height is 1 over 3.5. So 1 over 3.5 times it with times 2. Actually, no. Times it with, I want this area, right? 4 minus 2. Yeah, it's 2 then. It's closer to here. 2 times 3.5. 2. I have this. So I was, yeah, okay, I got it right. 0.57, yeah, whatever. The next question is, find the probability that a different 9-year-old eats a donut in more than 2 minutes, given that the child has already eaten the donut for more than 1.5 minutes. So given that this has happened already, 1.5 minutes took place already, right? Let me think. Okay, I think I have an idea. Probability that he will take more than 2 minutes. For more than 1.5 minutes. Given that he has already taken up 1.5 minutes, is probability of more than 2 minutes in general. Uh, um, okay, wait. If it's uniformly distributed, this area, wouldn't that, wouldn't then it mean that 1.5, the new probability is now like this? 4 minus 1.5 is 2.5. So we have this and white base. Let's see, which is 0.8, 4/5. Yes, yes, that's correct. Second question has condition probability. Since you know the child has already eaten the donut for more than 1.5 minutes, no longer starting at a is equal to 0.5. Okay, yeah, that's what I did. The exponential distribution. Exponential distribution is often concerned with the amount of time until some specific event occurs. For example, the amount of time beginning now until an earthquake occurs has an exponential distribution. Other example includes the length in minutes of long distance business telephone calls, the amount of time in months a car battery lasts. Values for an exponential random variable occur in the following way. There are fewer larger values and more small values. For example, the amount of money customers spend in one trip to the supermarket follows an exponential distribution. Okay, so let X be the amount of time postal clerk spends with their customer. Time is known to have an exponential distribution with an average amount of time equal to 4 minutes. X is a continuous random variable as time is measured. It is given that mu is equal to 4 minutes. To do any calculation, you must know m, the decay parameter. M is equal to 1 over mu. Therefore, m is equal to 1 over 4, which is 0.25. The standard deviation is the same as the mu. The probability density function is me to the power of minus mx. Okay. Using the information in example 5.7 and the probability that a clerk spends 4 to 5 minutes with a randomly selected customer. So between 4 and 5, right? And that's the area under the curve. We need integration for this. So we need to integrate this. We need to integrate this between 4 and 5, given that m is equal to 0.25, right? Cumulative distribution function gives the area to the left. So Px less than some value x is equal to this. Wait, did they give the formula for cumulative distribution? No, they didn't. But I have to keep in mind that the CDF is equal to this. Probability less than 5, probability less than 4, and then, okay, this minus this. Yeah, that makes sense. Half of all customers are finished within how long? 4 minutes? 2.8? Isn't the average 4? Mu is 4, right? So 4 minutes. Time is known to have an exponential distribution with an average amount of time equal to 4 minutes. So isn't that the 50th percentile? I do not understand this. Shouldn't it be the mean? Shouldn't mean be the middle value where it cuts off the areas to 50-50 parts? Or is that only for the uniform distribution? Okay, I think I'm getting confused. The value that cuts it 50-50 is not the same as the mean. I think I got confused there. Mean is just the mean is just the mean mu is just you have the probability density function. And the area gives the probability. So x times height width. This part is the area, and we multiply it by the value x. F of x dx gives the area, which is the probability. The sum of all this, um, yeah, the sum of all this would give the mean, right? This is not the same as cutting the area 50-50. Which is larger, the mean or the median? And the median is 2.8, mean is 4, the mean is larger. Yeah, the mean is larger actually. On average, a certain computer path lasts 10 years. The length of time the computer path lasts is exponentially distributed. What is the probability that a computer path lasts more than 7 years? More than 7 years. So, example 5.9. On average, it's 10. So then m is 0.1. So the probability distribution function is m e to the power of minus mx. So what are we trying to find? What is the probability that a computer part lasts more than 7 years? The cumulative formula CDX is 1 minus mx. And let's just write 0.1. So 7 is equal to 0.7. Probability is more than 7. So 1 minus this. Is that correct? Okay. And just go to the wait. Memorylessness of the exponential distribution. Recall that the amount of time between customers is exponentially distributed with a mean of 2 minutes. Suppose that 5 minutes have elapsed since the last customer arrived. Since an unusually long amount of time has now elapsed, it would seem to be more likely for a customer to arrive within the next minute. With the exponential distribution, this is not the case. The additional time spent waiting for the next customer does not depend on how much time has already elapsed since the last customer. This is referred to as the memoryless property. Specifically, the memoryless property says that Px r plus t, if x is more than r, is equal to probability of x more than t. I see. So what they're saying is we have r, we have t. So if r already happens, right? If r already happens, let's just take this graph. Let's just take this graph and then shift it back. So we have this. So the memory property says that if R happens, this part we don't need to be concerned about. Can start it from here. And then R, probability of R plus T. Probability of R plus T. Probability of R plus T. So this is the probability of more than R plus T. given that R has already happened, is equal to probability of more than T. And refer to examples 5.7 where the time a postal clerk spends with a customer has an exponential distribution with a mean of 4 minutes. Suppose a customer has spent 4 minutes with a postal clerk. What is the probability that the customer will spend at least an additional 3 minutes with a postal clerk? So the decay parameter of x is 1 over 4. Yeah, 4 minutes, that makes sense. And the cumulative distribution function is this. You want to find probability more than 7 given more than 4. And then this probability, okay, so according to the memory, this probability, this is equal to more than 3. And then more than 3, we just know how to find it using this. It's e to the power of minus 0.75. There is an interesting relationship between the exponential function and the Poisson distribution. Suppose the time, I said exponential function. Between the exponential distribution and the Poisson distribution, suppose that the time that elapses between two successive events follows the exponential distribution with a mean of mu units of time. Also assume that these times are independent, meaning that the time between events is not affected by the times between the previous events. These assumptions hold, then the number of events per unit time follows a Poisson distribution with mean lambda, which is 1 over mu. And the formula is this: lambda to the power of k to the power of minus lambda divided by k factorial. Conversely, if the number of events per unit time follows a Poisson distribution, then the amount of time between events follows the exponential distribution. What is the next chapter? Yeah, we'll just read this. At a police station in a large city, calls come in at an average rate of 4 calls per minute. Assume that the time elapses from one call to the next has the exponential distribution. Take note that we are concerned only with the rate at which the calls come in. We are ignoring the time spent on the phone. We must also assume that the time spent between calls are independent. This means that a particularly long delay between two calls does not mean there will be a shorter waiting period for the next call. We may then deduce that the total number of calls received during a time period has a Poisson distribution. Find the average time between two successive calls. Calls come in at an average rate of 4 calls per minute. So I'm guessing average time is half a minute. So in 1 minute, you expect 4 calls. Okay. Let me 4 calls per minute. Find the average time between two successive calls. Curve between successive calls. Oh, okay. I got it wrong. 4 calls per minute, 15 seconds in between. So it's a quarter of a minute. Assume that the time elapses from one call to the next as the exponential distribution. Find the probability that after a call is received, the next call occurs less than 10 seconds. Okay, let me just get rid of this. Sample 5.13. Call is received. So we have P, not P, probability density function is m e to the power of minus mx. The average rate of 4 calls per minute. 4 calls per minute. So I will just do this 1 over 4. And the cumulative is take note that we are concerned only with the rate at which calls come in ignoring the time spent on the phone. You must also assume that the time spent between calls are independent. This means that a particularly long delay between two calls does not mean that there will be a shorter waiting period for the next call. Next call occurs in less than 10 seconds. After a call is received, the next call occurs in less than 10 seconds. Average rate for, I think the average time between two successive calls, which they said is 0.25, I think that is our average. Mu is 0.25. That means M is 4. M is 4. Next call occurs in less than 10 seconds. So we are finding the probability less than 10 seconds. This is what? What did we find? 0.25 minutes for the next call. 0.25 minutes. So 60 seconds is 1 minute. I divide this by 60, 10 seconds is, I divide this by 60. So then 1 over 60. Sorry, I divide this by 6, I mean. Divide this by 6, so 1 over 6 minutes. 4 over 6. E to the power of minus 4 over 6. 0.4865. Is that correct? 0.4866. Okay, that is correct. And the probability that exactly 5 calls occur within a minute. Less than 10 seconds. Exactly 5 calls occur. I should call this F1 P1, P1, and then mu1. And then mu2 is 4 calls per minute. 4 minute per call. Then f2x is 1 over 4. Divided by 4. They're asking for exactly 5 calls. Wait, what? Exactly 5 calls. Exact. They said it follows a Poisson distribution, right? And then lambda we know 4 calls per minute. So we can plug in 4 and 5, right? Where is it? Yeah, we can just plug in 4 and 5. Yeah, we'll just go to the next chapter now. Oh, this is just an exercise. Okay, it has been an hour though. So I will end my stream here and yeah, I will see you guys next time. Also, I need to derive the mean and standard deviation for those functions and write it in my website. Anyways, I will see you guys next time then. Bye.